Aside from just describing data sets or allowing us to visualize the data we've collected, descriptive statistics are really the first step in any statistical analysis. And there's two primary components of descriptive statistics. One is being able to identify the central or typical value of the data we've collected. And then we also need to be able to describe the spread about that value. When describing the central tendency, there are really three primary metrics that we use, and which one you use is dependent upon the type of data that you have. So we'll start with the mean or the average, because this is really the most common metric used to describe central tendency. And as most of you probably remember, it's simply the sum of all of the data values you've collected for a particular variable. You sum all of that up and then you divide it by the number of observations. What you might not be as used to seeing is the statistical notation for this. Okay, so when we are working through formulas, statistical formulas, you're going to see a lot of the same symbols coming up. X bar is what we use to represent the mean or the average, and we just call it X bar. X typically represents an observation. The sigma symbol you should recognize as just instructing you to take the sum of whatever follows it. So this would be the sum of all of the x's, all of the observations. And a lowercase n usually represents the sample size. So this is really saying the exact same thing as we said in our words. We are going to calculate the mean by taking the sum of all of the observation values and dividing it by the number of observations. Typically, you're going to be calculating the mean either in Excel, if you're working in Excel, and there is a function that we can call in Excel to calculate the mean without even having to go through each of these steps. We can just type in the words equals average and then parentheses and then highlight the array of cells that we wanted to take the average of. So in JUMP, how does it work? From the main toolbar in JUMP, you'll go to the Analyze tab, and then within that, Distribution. And when you do that and enter whatever variable it is you're looking for the mean on into the little Y box, it will give you some output that looks like this. So JUMP is always going to give you a visual, some graphic of your data, right? And then it also gives you a lot of other information. It sort of guesses what it thinks the most common descriptive statistics are that you would want. So notice that we have all of our quantiles here, but we also have the mean right at the top of the summary statistics. And then it gives us also standard deviation, standard error, our confidence intervals, and our overall sample size. As I mentioned, mean is the most common metric, but it's not always the best metric, and this is especially true if your data set has any extreme scores. So either very high or very low scores relative to most of your data are going to skew your data to one side or the other. And so this makes the mean not necessarily a very good metric if you have skewed data. Other instances when the mean is not necessarily the best option to describe the central tendency of your data is when each of your observations may not have an equal weight, or you might not want to give them an equal weight. A really good example of this is the adaptive cluster sampling technique that we had just talked about in our last module, our experimental design module. You know that you hit a certain value at your original sampling point, but then you're going to take measurements in clusters around that sampling point. Now those may not be weighted as heavily as that initial measurement. So this is one way of trying to get at and still represent a population even though you're cluster sampling. Another example might be if you're taking measurements over a certain duration, and maybe, for example, you're summarizing bird counts and the number of times you hear birds of different species singing. Maybe you had somebody who was out for 10 minutes at one spot, but then they ended up spending 15 minutes at another spot. That might be an example of when you would want to weight those individual observations at a given location by how much time had been spent collecting that data. This still looks very similar to the calculation for the arithmetic mean that we just went over, except we have one new term inserted, and that's the weight, and the little sub I represents each individual observation. So this weighted, the X bar sub W, the weighted mean, is simply the sum of every observation multiplied by its weight, right? So the weight for observation I multiplied by the value for observation I. And then you're going to divide that by the sum of all the weights. So you're no longer using the number of observations, you're just using the sum of the actual weights. So when the arithmetic mean is not appropriate, perhaps because you have skew or these extreme values in your data, and the weighted mean isn't appropriate because each observation is equally weighted, the metric that's typically used is the median or the middle value. And there's no fancy formula for this. You simply put all of your data in rank order, so from lowest to highest, and you look for the middle score, okay, the middle score across that whole data set. We'll just give a really simple example. Imagine we have this data set. If we first put those all in order from lowest to highest, we see that we have 15 observations, right? So the middle observation would be the 8th. That means we have 7 observations on this side and 7 observations on that side. So the median would just be the value of that middle observation. Now, if you're in Excel, you don't have to go through all of that. You can simply use the function equals median, and then again use your parentheses and highlight the array of cells that you want the median value for. Close bracket that, and it will just report back your median value. In JUMP, you find the median from that same platform that we got the mean from. It's just in a different spot. It's right up here listed within the quantiles. There would be the median. So Excel and JUMP will both figure this out for you, but if you had an even number of observations, so there was no middle value, you simply are going to take the mean of the two nearest the center, right? So in this case, the median would be 22. Back to the JUMP output for a second. So notice how there are quite a few different quantiles listed in the JUMP output by default, not just the median. Percentiles are used to quantify the value below which a certain percent of that sample or of all of the total observations would fall. Statistically, there are some specific percentiles that are of use to us. In Excel, if you're actually trying to find the percentile for a given value, you can just use the percent rank function. Now, I know this is counterintuitive because you're asking for a percentile, right? You wanted to calculate a percentile, but the function that you use is actually percent rank, okay? So equals percent rank, put in your parentheses, highlight the array of data that you want it to use, place the comma, and then put in your value of interest, so whatever that value is that you want the percentile for. Okay. The flip side of that, if you actually want to know the observation value for a given percentile, right? So now we're looking for the observation value. You would enter equals percentile, put your parentheses in, highlight your array, comma, and now you would enter K, and K is going to be the percentile that you're looking for. Note that this is on a 0 to 1 scale, so you're going to be entering a decimal, right? It's not on a 0 to 100 scale like we were using in the original formulas. As we saw before, in JUMP, that standard output from the Analyze Distribution tab will give you some of your percentiles. These are predetermined based on what we might commonly want for some of our statistical analyses. But we can pull any percentile out that we want. We just need to go to the magic red triangle. So if you've done the tutorial, you would have figured out that almost anything you could want in a JUMP analysis is going to be buried in one of these little magic red triangles. And from the list that we have here, we just can go to the display options and ask for some additional display, including custom quantiles. We can actually enter the quantile that we're looking for, or we can just set a quantile increment. So in this example, I set the increment to 0.05, so it gave me every 5% increment from 0 to 100. So while we can pull out any specific quantiles we're interested in, JUMP by default does give us some standard quantiles, right? And these are quantiles that are commonly used for other statistical applications, and one great example is in outlier detection. One common approach to identifying observations that might potentially be erroneous or at least are outliers based on the larger sample you've collected is to use what's called the interquartile range. So what we're doing there is we're just looking for that value for our third quantile and our first quantile, and we subtract the two of them to come up with really the range of values within which 50% of all observations fall. That's our interquartile range. It's pretty common to take this interquartile range and expand it a little bit, usually 1.5. So you take 1.5 times the interquartile range, and if you subtract that from the first quartile, right, that 25th percentile, and add it to your third quartile, so essentially you're taking your interquartile range and you're expanding it out 1.5 times from each of the edges. What that does is it gives you a value, a threshold, below which or above which any observations are suspect outliers. And JUMP does this and gives you the visual as well. So you can see the first quartile is the lower bound of the box, and the third quartile is the upper bound of the box. And then these little whiskers are that 1.5 times the interquartile range. Any observations that fall outside of that are going to actually be highlighted as a dot in your histogram distribution figure. Another common approach to using quantiles to identify outliers is just to use the 0.5th and the 99.5th percentile, and those are actually given to us by default in JUMP. So these would be sort of a secondary threshold that you could use to identify your outliers. So all of the central tendency metrics we've covered so far are really most appropriate when we have continuous data. Right? But when you have ordinal data, so data that has an integer value, it's really not as common to see a mean or a median even used. Typically, you'd see a mode used, what is the most common value that shows up in our data set. In Excel, you can use the mode function. So you just enter equals mode, you parentheses, and then highlight the array that you want to have the mode returned for. But the problem is that this will only return the first or the lowest value. But there are often times in data sets where you may have more than one mode. So these are considered bimodal distributions. And this is why it's always important to graph your data first, and why JUMP always gives you that output where it gives you the histogram of all of your data. You also might encounter a situation where there's no one value that occurs more than once. So you really essentially have no mode. So Excel isn't going to pick up on things like that, which is why when you're in Excel, it might actually be best to use a pivot table to break down your data and identify how many observations you have for each potential data value. In JUMP, you have to dig a little bit deeper to get the mode, and again, we go to the magic red triangle, and this time we ask for the summary statistics box to open up. And from the customized summary statistics window within that, we can select exactly what information we want included in the output, the summary statistics output that show up in our original analyze distribution window. So we can just click on the mode, and then that will be added to the output. So just to summarize when to use what, just know that right off the bat, you're always going to use the mode whenever you have categorical data, or the data is coming in as integers, not as a continuous variable. Okay, then you want to use the median if you have a continuous variable, but you likely have extreme scores or non-normally distributed data. The rest of the time, you can just default to the arithmetic mean. Probably good to take a moment and just think about how each of these different metrics of central tendency are related to each other. Okay, most data is normally distributed, particularly in the world. Nature loves norms. So most of the variables that we'll be collecting will follow some sort of a normal distribution, this bell-shaped curve. And when you do have a normal distribution, your mean, your median, and your mode, they all line up, right? They're all really in about the same place. But it's when you have skew that you start seeing them pulled apart. So remember, the mean is the metric that's most influenced by extreme values. So if we have extremely high observation values, our mean is going to be pulled away from the mode and the median and stripped down to this positive skew in the positive direction. If we have extreme values down at the low end, it's going to pull our mean down towards the negative direction. Okay, again, the mode typically stays at the peak of the curve. The median is affected less by those outliers. But really, you can tell whether or not you have a positive or a negative skew just by comparing your mean and your median. If your mean is really different from your median and it's much lower, then you know you have negative skew. If your mean is much higher than your median, then you know you have a positive skew. And in the next section, we'll get into some more scientific ways that we can test for significance of skew. So we'll leave that for now for central tendency, and we'll get into variance in our next video.